All right. Hi, everyone. Welcome to week 12 of Mathemagic Mentors, our MCA prep series. Today, we'll be covering a really fun topic called modular arithmetic. And it relates to counting in a very close manner. But as you'll see, this presents a really cool, really fun way to think about numbers in a different way than you would usually see in school math, and this will obviously help with a lot of contest math problems, especially in the MCA. So without further ado, let's get started. Feel free to drop any questions that you may have about any of the topics, um, and I'll be happy to answer them. All right, cool. So let's think about let's first cover what exactly is modular arithmetic before we even think about like how we're going to apply this concept to more creative problems. So let's start off by thinking about just counting in general. So let's say let's start with one. All right, let's say we have a list of numbers, and we're going to count upwards from one, and we're just going to count every integer uh, just by increasing the previous number by one. So we're just gonna go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Right? So very straightforward, nothing new about that. But the new idea and what modular arithmetic introduces is that there are only a limited number of possible values that a number in this we call it like modular system can take. So what this means is that like that's again taking our regular list of numbers. If we keep on counting from 10, right, we're going to obviously have 11, 12, and then so on. We're going to have an infinite number of possible values that a number in this list can take, because it can be like 1,000, it can be a 10,000, etc. But now with modular arithmetic, if we let's consider a new type, a new list of numbers. I'm just gonna write it in red. And what if it goes something like 1, 2, 3, 4, but the fives, six, like anything above five doesn't really exist. So what would happen here? Well, modular arithmetic is going to tell us that once we get up to 4, the 5 is going to become a 0. And interesting enough, and we'll see why in a second. So 5 is gonna become a 0. 6 is gonna become 1 above a 0, which is just gonna be 1. 7 is gonna become a 2. 8 is gonna become a 3. 9 is gonna become a 4, and then 10 is gonna wrap around to 0. So again, you're gonna see the cycle of values that instead of seeing like all those different numbers that you would normally see when you count upwards from 1, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, you're going to just have a certain set of values that that numbers can take. So what we normally associate 5 with actually become 0, 6 will become 1, 7 will become 2. So in this newly defined number system, we're only going to have numbers from 0 to 4. So the numbers will only be in the set 0, 1, 2, 3, or 4. It can only hold one of the 5 values. All right. So this kind of notion like might seem a little crazy to you. Like, why does the 5 like suddenly become a 0? And like that seems really arbitrary. Why do we do that? So the easiest way to think about it is through a clock analogy. So if I were to present you a clock, right? You know how the numbers on the face of a clock is represented, right? So you have 12 on the top, and then it goes from 1 all the way to 11 as you go clockwise. And so if we replace the 12 on top with a 0, let's see how we can reproduce a list that looks very similar to the list in red that we developed over here, right? So if we start here, let's start at this start point on top, which represents 0. So if we were to just hop one spot clockwise when we count up by 1, we're gonna produce something like this. So first we're gonna write 0 just as the first number. Now we're gonna hop clockwise, one spot clockwise. It's gonna be 1, and then 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So I was just verbalizing all of these moves that I'm drawing here with the arrows like that. Oh, not this one yet. So once we hit 11, something really interesting happens. Because remember that, like, when we started at 0 and counted up, it's just naturally is how we would count in our base 10, like um, normal number system. But when we hit 11, we're gonna instead instead of counting to 12, we're gonna loop around back to 0. So it's going to be a cycle. So once you hit 11, the next number above 11, if that even exists, is going to be 0. So that's what happens when we count upwards. It's just going to keep on cycling and cycling. And so the next number, like in the sense that you would count upwards after 11, will be 0, and then 1, and then 2, and then 3, all the way when you wrap around to 11, it's going to come back to 0. And so an interesting question is, like, how many moves on which number of the clock will I end up with after 12 moves? And so since after 11 moves, you've counted up to 11, right? So after 11 moves, so on the 11th move, you're going to be at 11. On the 12th move, right, we there's no number that says 12 here, so it's just going to simply be 0, just because of how we designated this clock. And so thinking about this, right, we can say that if we draw a clock like 0, 1, 2, 3, 4, we can see how the list in purple or pink corresponds to the list in red, because we see that, okay, if we start at 0 and we consider the number that we end up after however number of moves, we can see that the 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 value of the red, the current value of the red, uh, the number in the red list will correspond to the value on the clock that after n moves will end up with. So for example, if we take the pair, if we take, like, let's say here, right? This is basically saying after 7 moves, right? We're gonna end up at the 2 right over here. And we say the same thing with any other number, right? If we keep listing this out, after 12 moves, after this basically says after 12 moves, we're going to end up at 2. We're going to actually end up at the same number as we did with 7 moves. And then same with 2 moves. So all of this comes down to the concept of remainders. So you may have recalled, and we're going to make the connection here between, like, counting the clocks and the remainders, and it will all make sense in a second, right? So if you're dividing, let's take a really simple example because we want to make it simple. This concept, again, is a little new, so we're gonna have 12 and divide by 7. So 12 divided by 7. How are you gonna compute that? So as you learned, well, how many times does uh, 7 go into 12 just one time. And so subtracting 7, we're going to have 5. And so since 7 can't go into 5, we're going to have a remainder of 5, as you may have studied in previous math classes. So we can say that 12 divided by 7 gives a remainder, gives a quotient. Let's say I'm just going to denote as Q. So quotient of 1, remainder of 5. And so modular arithmetic gives us a really special notation for this result. And so when you think about modular arithmetic, usually one really useful concept is remainders. So whereas like you may have been paying attention to quotients, so like what is the result when I divide one number by the other, right? That's you're most likely to get a quotient. But obviously sometimes one number doesn't exactly divide into the other and you're going to have remainders. And so with modular arithmetic, the main idea behind that is considering the value of remainders. So we can say that 12, this is the new notation. I'll just cover it here. I have a separate section for that. But this is the key idea this is the main notation um, that is going to be very important. So with modular arithmetic, the how we denote modular systems on that is that we say 12 is congruent to 5 mod 7. And you should probably write this down or just take note of it, because this is the main idea and if you could get one thing out of this, along with the analogy that we covered above, you would want to know exactly what this means. So 12 is congruent to 5 mod 7. And so I'm just going to write it down. 12 is congruent to 5 modulo 7. So the mod denotes modulo. And so this basically tells us that the remainder when 12 is divided by 7 is 5. And so the mod that you see here basically denotes the remainder. And so the number that goes to the right of the mod, so mod something, is what you're dividing by, and the number that goes to the left of that will denote exactly what remainder you're going to get. And so that's very apparent when you compare our notation to the division that you see to the left. So when you divide 12 by 7, you're going to have a remainder of 5. And because we're dividing by 7, we can say that 12 is congruent to 5 modulo 7. So how does this relate to our clock analogy? Well, we can actually say that the corresponding numbers on the top list and the bottom list that we see over here, so the list in the pink and the list in the red, are congruent modulo 5. So if we take this list, this purple list, and then we take the remainder when every single number in this list is divided by 5, then we're going to end up with the red numbers that you see below. So with the green highlighted numbers, let's just take, for example, this starred pair. We can say that 7 is congruent to 2 modulo 5, because it is true that dividing 7 by 5 will give you a remainder of 2. Again, you can do this for any number in the list, like let's say like 9, right? You can say that 9 is congruent to 4 modulo 5. And that will also be a true statement because when you divide 9 by 5, you're going to have a remainder of 4. And with the clock analogy, it's just a really just a really nice, simple way to like think about remainders. And so, since there are only 12 possible, like 12 possible numbers on the clock, you're going to obviously have 12 possible remainders, and that will obviously be the results, be the possible remainders when you divide by 12. All right, cool. So we already covered the notation. Let's cover some basic properties of modular arithmetic. And so I'm just going to write it down here again. So if we say that A congruent to A is congruent to B mod C, we're just going to say, we can say that A, the remainder when A is divided by C is B. And in fact, modular arithmetic, it doesn't actually give us like a fixed value of B. So when you think about this, will be, I guess this will be a future topic, but when you think about the let's say you take these pairs, right? 2 7 and 2 7 and 12, we can actually say that like 7, if we want to say 7 is congruent to what mod 5, obviously you can do the remainder thing and get 2. But we can also say that 7 is congruent to 7 mod 5. Although it is not true that we get a remainder of 7. And so we'll be discussing that in a few moments. So before we do that, we're going to cover some basic properties that you should definitely know. And so these basic properties explain what happens when you add, subtract, multiply, or divide by numbers in modular systems. So for now, I'm going to assume, to establish our properties, assume that A, B, let me think. Actually, I'm just gonna denote these as the following: A1, B1, A2, B2, and C. Okay, these are all variables, and they're going to be integers. And we're also going to assume that A1 is congruent to B1 mod C, A2 is congruent to B2 mod C. And so what can we say if that is true? Well, this is where we can establish our properties of addition, subtraction, multiplication, and we can't really do division. Division is gonna be handled a little bit differently. So let's do addition. So let's say we want to get the result of by adding the two numbers. So as similar to adding like both sides of the equation in linear equations. Like if you have 3x equals 2 and like 5y equals 7 in like a separate case, you can obviously add them to get 3x plus 5y equals 2 plus 7, right? You can do the same thing with modular arithmetic. And so you can say that a1 plus a2 is congruent to b1 plus b2 modulo c. All right. And we'll show you how ways that we can simplify this. But again, you should know this property for a modular arithmetic. So subtraction, same, like if we want to subtract a2 from a1, it's kind of like the same thing with addition. We're just going to have a1 minus a2. I'll zoom out a little bit so we can see the assumption. A1 minus a2 is congruent to b1 minus b2 mod c. So remember, when we use modular arithmetic, we're going to use these three dashes instead of the equal sign. And it's because we're not saying that this quantity is the same thing as that quantity. It's the same thing modulo c. It's the same thing in another base system that we're considering. And so always keep in mind to use three dashes. And so with multiplication, I'm just going to say multiply. You get the same thing. A1, A2, or that rather the same form, is congruent to B1, B2 mod C. And again, A1, A1, A2 is just the same thing as A1 times A2. And those are the three basic properties. There's some other properties that are more trivial that we won't be diving into detail, but obviously you're going to see that in problems, so you naturally pick them up, like a1 times 0 is like 0 or stuff like that. But in my opinion, the main three that you need to know are these three. So how do we let's like play around with modular not necessarily modular equations, but rather modular expressions. So how do we handle them? Let's look at a few examples here, and Sid will pick up with more advanced tactics. And so let's think about the expression, I don't know, 12 plus 3. So let's say you want to simplify 12 plus 3 like modulo 5. So this is really interesting because what do you get? So if we want to simplify 12 plus 3 modulo 5, obviously we can just add them, because remember that with our previous property here, we can always add numbers in a modular system, get some result, and then do something else with that. And so if we want to simplify 12 plus 3 mod 5, we can just add it. And so what is 15 modulo 5? What is that? So one way to think about it is the remainder when 15 is divided by 5. So since 15 divided by 5 is 3, remainder 0, and as a remainder of 0, we can just say that's 0. And so 12 plus 3 is 0 mod 5. We usually write the mod 5 everywhere, but yeah, it's 0 mod 5. So let's give another example. How would you simplify 47 mod 5? Is there well, actually, before I cover this, there's really one important concept to mention here. And so with a concrete example, let's consider the number 2, right? What is 2 mod 5? Well, 2 is just 2. 2 is just 2 mod 5. Because when you divide 2 by 5, you're obviously going to get a remainder of 2. Because 5 is just too big to actually fit in 2. And so it's going to have a remainder of 2. What about 7? Well, we can just do it. We can just do the remainder with a division. So 7 divided by 5, you're going to have 1. Subtract 5, that's 2. And then 2 is obviously too big, so we're going to have a remainder of 2. 1 remainder of 2 when 7 is divided by 5. So we can say that 7 is congruent to 2 mod 5. And what about 12? Well, do the same thing. We're actually going to get a remainder of 2. And so there's something really interesting happens with modular arithmetic. Because remember, because like if you think about it, if we're adding 5 every time starting from 2, but we're always getting the same result modulo 5. So the remainders, when we add uh, the numbers by a multiple 5, like they all give the same remainders when divided by 5. So in fact, we call this a residue class. Residue. The name is really not too important, but it's very important. But the main idea that I want you guys to see is that 2 is congruent to 7, is congruent to 12, and then what would be the next number? Well, we added 5 to the previous number every time that we wanted a new number. And so we can just add 5, and 12 plus 5 is 17, and then so on. And then you can just do this, keep on doing this process of adding 5. You're going to get all of these numbers are congruent to 2 modulo 5. So we can say that this is the residue class of 2 mod 5. I think there are some important properties that I think I kind of forgot, but this establishes a really important one that's outside of our basic like addition, subtraction, and multiplication properties, which is that if A1 is congruent to B1 mod C, we can add or subtract a multiple of C. So whatever we're dividing by, and do the same thing with the right hand side. And KC basically denotes a multiple of C. So it's a little bit mind-boggling to think about, but again, if you have any questions, you can always feel free to ask in the chat. And so with that idea in mind, we can start simplifying problems really easily by basically just taking the remainder of really big numbers when we're dealing with them. So I'm going to go up here. I'm just going to show you a quick example of how we can do this. So if we have, let's say we want to find the remainder when 47 is multiplied by 53. We'll find the remainder when this product is divided by 9. Right? So remainder. This modular arithmetic, it really simplifies problems when you're asked to find the remainder of something. Because let's consider these numbers mod 9, because we're asked to find a remainder when this product is divided by 9. So we want to find 47 times 53 mod 9. So, okay, so we're working mod 9. I'm just writing that right here. So what is 47 mod 9? 47 mod 9, let's just do the remainder real quick, because we want to find the remainder when 47 is divided by 9. So we can do a 5, subtract of 45 gives us 2. So 47 is congruent to 2. Remember that when we're dividing, we're just basically whittling down all of those multiples of 9s. And so that's why we can find the remainder. So 47 is congruent to 2. We do the same thing. I think 5, yeah. And then you're going to get 8. And then this is 16, because 2 times 8, we just simplified 47 to 2, 58 to 3 by subtracting multiples of 9 by via division. And 2 times 8 is going to be 16. And then obviously we can just subtract a multiple of 9. Remember that subtracting and adding a multiple of the modulus, so like if we're taking mod 9, adding or subtracting 9 doesn't really affect the final value, which is like really nice. And one of the most basic properties of modular arithmetic. And so subtracting 9 from 16 will give us 7 modulo 9. And so since 7 is less than 9, we always want to find, when we ask to find the remainder, we want to find something that is less than the modulus. So in this case, it will be 9. So since we found a number that's less than 9, 7, that is our answer. And so the remainder, when 47 times 53, it's divided by 9, is 7. And there you go. That's some basics of modular expressions. I'm going to hand it off to Sid to explain further if some other concepts regarding modular arithmetic. Thank you, guys.
All right. Thank you, Daniel. Hi, guys. So I'll be covering some different types of modular equations and then moving on to more concepts. So I'll just share my screen here. Can you guys see my screen?
Yep, it's good.
All right. So, um, so uh, keeping what Daniel said so far in mind, we'll go over some types of modular equations where basically modular equations are a way of like a way of expressing expressions where there could be multiple residues for a certain modulo m, right? So for example, say you have the congruence, that's x plus 4 um, is congruent to, so let's say 6 mod 7, right? And so a way of doing, actually let me go over a much simpler modular equation that'll help us get introduced to this topic. So a simpler modular equation could be 2x is congruent to 1 mod 5. And so what this means is that we have to look at all the different x's that make this certain congruence true. And so that could be and that could be one specific value of n, one value of x. But as we'll see, there is actually multiple values of x that could satisfy a certain type of modular equation. But in this case, 2x is congruent to 1 mod 5. Does anyone kind of see how we can get started on this? So the way to do this is that first of all, you realize that you want to look at all the different values of x that range from 0 to n minus 1. So 0 to n minus 1. So that's in this case 0, 1, 2, 3, 4, right? And why I say from 0 to n minus 1 is because when you have and so you have 2 times n, and then you do that, and so basically the cycle repeats, as Daniel showed you guys with the clock example, where um where if you have 0 mod, well, if you have some number mod m equal to 0, so if I had say x here, if x was so 2 times 0 is 0 mod 5, and 2 times 5 is also 0 mod 5, because the cycle repeats exactly after 5 integers. So 0 mod 5 is exactly the same as 5 mod 5. 1 mod 5, 1 mod 5 is exactly the same as 6 mod 5. So we actually don't have to look at values that are larger than n minus 1, or here 4. Because when you look at values that are larger than 4, the cycle basically repeats and you're just basically wasting time. Um, so in this equation, as we see, 2x is congruent to 1 mod 5. Well, the thing to notice here is that unfortunately this equation is just not viable, because the reason why is because 2x is gonna give you an even integer, right? The 2x is gonna give you um, basically zero. All any even integer, any even number or integer is gonna give you 0 mod 2, or yeah. So any even integer is gonna give you some some 1 mod something, right? So the reason why this, or actually we can just move through the values and see why it doesn't work. So we have we have 2 times 0, which is congruent to 0 mod 5, and so obviously that doesn't work. How about 2 times 1? That gives you 2 mod 5. Well, that doesn't work, right? How about 2 times 2 gives you 4 mod 5? Well, that doesn't work. How about 2 times 3? Now this works, right? Because it gives you 6 mod 5, but 6 mod 5 is congruent to 1 mod 5 as well. And then 2 times 4 gives you 8 mod 5, which is congruent to 3 mod 5. And so the only thing that works here is 3, right? X equals 3. But the reason why I chose this problem is because is to just show you guys that there could be multiple different values of x that works here. Now, we saw that 3 worked here, but what if we want to, well, again, remember what I said about a modular equation. A modular equation is just not just one value, one type of value. It's multiple types of values, right? That satisfy this equation. It's not just 3, it could be anything else, right? But as we saw, 0 is not going to work. Any number mod 5 which is equal to 0 is not going to work. Any number mod 5 which is equal to 1 wouldn't work, and so on. So what could work, right? X equals 3 could work. And so as we'll find out, how about x equals 8? Well, 2 times 8 is going to give us 16 mod 5, which is congruent to 1 mod 5, right? And so what do we see here? We see here that x equals 3 works, x equals 8 works. And so can you guys find a pattern between all the different numbers that could work here? Uh, so for me to write these families of numbers that like satisfy this modular equation, it look something like 3 plus, yeah. If you have questions, just type them in the chat and Daniel will address them. So if I want to write all the numbers that satisfy this equation as a family, it could look something like 3 plus 5n, where n is any integer. So those are all the different types of numbers that'll work here in 3 plus in this equation basically. So 3 will work, 8 will work, and then 13 will work, and then 18 will work, and basically so on. Does that make sense to everybody? Just again, type your questions in the chat. And now I'm gonna show you guys another type of modular equation that could work with some simplifying. So if we have something like x plus 4 is congruent to, let's say, 6 mod 7, right? So how would you go on solving this modular equation? The way you'd go on by solving this modular equation is actually using something that Daniel mentioned earlier on, which is using the subtraction property. So that means that if x plus 4 is 6 mod 7, I know that I know that x if x plus 4 is 6 mod 7, I know that x has to be 2 mod 7. Why? Because if I subtract 4 from both sides, I do get x is congruent to 2 mod 7. And again, this is something that you can kind of relate with linear equations, which we covered earlier on, and apply that to modular equations. So if so, both things work here, which is if you if you know if you know the property of linear equations, where you can simplify equations by subtracting equal quantities on both sides, the same thing applies here. So you can convert a congruence into something much simpler by simplifying both sides by either adding or subtracting quantities. So that's what we did here. So if x plus 4 is congruent to 6 mod 7, I have x is congruent to 2 mod 7. And now we can notice something interesting. So it says that all the different values of x that will satisfy this equation is all the different x's that satisfy x is congruent to 2 mod 7. But we already know how to express these types of numbers, as Daniel mentioned before. These are just these classes of numbers are, if you want to start with 2, that's fine. So we can start with 2, and we can say that these numbers uh, differ. All the numbers that x can be, all those numbers start from 2 and can differ by any integer, any multiple of 7, where n is some integer again. So you could go negative, and you could go positive, and that's fine. So that's our solution. X 2 plus 7n is uh is the solution to this equation where n is an integer. And just a last thing on modular equations before we go on to covering unit digit problems is that this is just something you could remember this, but this is just something if you're doing an EMCA problem that kind of requires you to think about modular equations, and you're kind of confused on how many residues you should look out for, because sometimes there could be. So let's say in 7, this is a very manageable case, because you only test out cases from 0 to 6. But let's say you went from 0 to 100, right? And you're asked to solve a modular equation. I don't know if you will, and I don't know if the AMCs will actually test you on that, but this is just something to know. The number of residues that can be that you can think of getting in these situations is m. I'm not gonna go over the proof, because it's just too long and it's beyond the scope of our time here. But the formula for that is m over GCD of n and m, where the equation's gonna be let's say Cn plus d is congruent to some x mod m. Basically, so in this case, we can actually test this formula out. We saw that we only have one residue, which is 2, and that's all that works, right? So so since this equation only had one type of residue, it's we can test it out. Basically, we have m as being uh so yeah. And so I'm not gonna go over that right now, but you guys can test it out to see if it works. All right. So time permitting, we're gonna go over the some unit digit problems. Oh, my bad. I just wrote everything in like under the last digit, but that's fine. So I'll go over some problems that are gonna introduce us to the unit digit concept. So first, we can start with this this problem, which is, let's say you had let's say you were supposed to find the units digit of number, let's say 7 to the 8, right? And you're supposed to find the units digit of that. What would you end up doing, right? So um, in order to tackle these types of problems, basically you'd look at simpler cases and try to see what happens from there on. And also, just something to remember is when you're considering unit digit problems, you always want to look at the number mod 10, right? And so we can kind of see why that works. It's because any number mod 10 will give you the remainder that, okay, so if you have a number, say 123, right? Any number, if you divide that by 10, it'll give you as a remainder, it'll give you this last digit, which is what the mod does, right? It gives you the remainder when you the remainder that you get when you divide this number by this number. And so if you have 123 mod 10, obviously 123 is not a multiple of 10, but if you divide 123 by 10, you get a remainder of 3. And as you see here, 3 is the last digit. And that's just because any number that has more than one digit, so like more than 1, 2, 3, 4, 5, all the way to 9, it's just 12 times 10 plus 3, and you're trying to calculate this mod 10. And what you can do is that you can actually um, like the way you it's just the way you calculate do normal algebra. It's you can actually express this as a distribution. So you can say 12 times 10 mod 3 mod 10 plus 3 mod 10, and you can see that this is 0 because 12 times 10 mod 10 is just 120 mod 10, and 120 mod 10 is 0 because it's perfectly divisible by 0 10, right? And you can easily see that 3 mod 10 is just 3. So the units digit is just 3. And so when you usually look at a units digit of a number, you usually deal with something mod 10. And so 7 to the 8 mod 10, if you want to look at that, we can look at 7 squared mod 10, which is 49, right? 7 squared is 49, but then that mod 10 will give us 9, right? But now, um, we can actually use exponents to, instead of just multiplying number after number after number, we can take use of the value of the, or of the we can take use of exponents, right? So what do you do when you get that? So if you have 49 mod 10 is 9, this is 7 squared mod 10. To get 7 to the 4 mod 10, that is just equal to 7 squared mod 10. And you can actually think about the mod 10 coming inside the parentheses, so inside of the squared term. And so you can get, so if you Try doing that. You'll see that it's 7 squared mod 10. And you can calculate that squared and then again mod 10, right? So if you do that, you get 9 mod 9, right? Because 7 squared mod 10 is 9. And then 9 squared mod 10 will give you 81. But then 81 mod 10 is just 1, right? Because 80 is a multiple of 10, perfect multiple of 10, and it leaves a remainder of 1. And then doing the same thing, you can see that 7 to the 4 squared mod 10 will give you 7 to the 4 mod 10 squared mod 10, which is 1 squared mod 10, which will just give you 1. So 7 to the 8 mod 10, or the units digit will give you the units digit of 7 to the 8 is 1. And so this is a really useful way of using modular arithmetic to come up with last digits or unit digit problems. And it's yeah and this use of exponents to simplify the problem down is something that will show up in a lot of AMC and AMC 10 problems. And so it's really useful and something that you should definitely keep in mind. All right. So now we'll look at some other problems, and these problems are actually more. Uh, these problems don't require like last digit properties, but these are still very useful to go into. So this first problem says Jerry has 44 boxes of soda in his truck, and the cans of soda in each box are packed oddly so that there are 113 cans of soda in each box. So, what's the total number of soda that Jerry has? Well, it's the 113 cans times uh times 44, because each box has 113 cans and then there's 44 of those boxes. So the total number is 113 times 44. And then it says Jerry plans to pack the soda into cases of 12 cans. After making as many complete cases as possible, how many sodas will Jerry have left over? And so there is a very, and so I guess there is a very glaring, glaring use of modular arithmetic to be used here. But it, but like you have to read the problem carefully and break down the problem into bite-sized pieces so that you can see exactly where the modular arithmetic is coming from. Right? So 113 times 44 is the total number of cans that we have. But we want to pack those cans into 12 boxes and then see how many are left over. So that means that our 12 boxes are gonna include like our 12 boxes, right, have to include, or our 12 or our boxes have to include 12 cans in each of them, which means that each box has to hold like, so that means that like n boxes will hold like 12 times n cans. And so that means that every can that's filled, as to say, is a perfect multiple of 12, right? Because every box has 12 boxes, 12 cans, and then those boxes, there are n of them, and so there's 12 times n. And so actually we can calculate this total number mod 12, because uh, that will take into account all the multiples of 12 that we have, and just leave out the remainder at the end, which is, or in this problem's words, how many, so this number of sodas that's left over, right? And so we can use something that Daniel said earlier on, which is the property of multiplication of two numbers while calculating mods, which is uh, 113. So you can break this up again into, you can think of this as say like a distributive property, right? And so you can think of 113 times 44 mod 12 as 113 mod 12 times 44 mod 12. And so 113 mod 12, well, we can think about the nearest multiple of 12 that there is to 113, which, just to save time, it's 108 because 12 times 9 gives you 108, right? And so we can see that 113 mod 12 is 5, right? Because uh, 108 is 5 away from 113, and 108 is a perfect multiple of 12. Similarly here, um, the nearest multiple of 12 that there is to 44 is 36. I'll just keep, by the way, I'm just trying to keep everything here in positive terms, and I'm not going to go into the negatives, but you could also say that this is like negative 4 mod 12 um, because 44, there is 48 that's higher than it, and so it's negative 4 from 48, and it's positive 8 from 36. But I'm just trying to keep everything positive here, so I'm just going to ignore the 48, and I'm just going to say it's 8 because 44 is 36, 8 away from 36, which is a perfect multiple of 12. And so if we multiply that separately, we get that this is equal to 40 mod 12. And so 40 mod 12, what's 40 mod 12? 40 mod 12 is 4 because again 36 is the nearest multiple of 12 to 40, and it's 4 away from 40, right? And so 4 is the remainder that you get. And so our answer is 4. So after completing all the different complete cases uh, of soda cans, Jerry will have 4 leftover sodas. And so before we go, I want to cover this one last problem, which says find the remainder of 7 to the 8 when it is divided by 100. Right? So that means that we have to calculate 7 to the 8 mod 100. And so if mod 10 gives you the units digit, mod 100 will give you the uh, tens digit and the units digit, because so you can figure this. So just because of time, I'm not going to go over it, but basically the hundreds digit of any number is whatever is in the hundreds digit and beyond times 100, right? And so the remainder is going to be the tens and the units digit, because that's what's left over when you divide anything by 100, right? So in 7 to the 8 mod 100, we can again go over 7 squared mod 100. 7 squared mod 100 is going to give us 49, right? And then you can choose to do 49 squared to get 7 to the 4 mod 100 and so on. But I'm going to go calculate 7 cubed mod 100, which is just going to be 49 times 7, which is 343 mod 100, and that gives us 43, right? And then 7 to the 4 mod 100 is going to be 43 times 7 mod 100. Oh, right? And 43 times 7 is going to give you 301 mod 100. And so you can square the 7 to the 4 and get 7 to the 8 mod 100, which is the 01 squared, will give you 1 mod 100. So the answer here is 01. And that's the remainder that you get when 7 to the 8 is divided by 100. And so I guess that's it for today. That concludes our session 12. We'll be sending out the problems and the homework problems and an outro email that'll also specify the next date that we are meeting and what we are covering. And
Right.
so, yeah,
Thank you so
that's it
much.
there.
And we'll be
Thank
sending
you,
out
everybody. Yeah,
the recording of the problems.
yeah. Bye.
Thank you, guys.